Hi dear friends, today we're going to talk about some news that life may have been discovered on an exoplanet, on a planet orbiting a distant star. It's about the planet K2-18b, and there they may have detected a molecule called sulfura de dimetyl in Romanian. And that molecule is produced on Earth only by living organisms, so that would be an indication that there might be life there. But is it really so? We're going to talk about this in more detail, and I've made a plan here that I'll share with you so you know what to expect. So first we're going to talk about the method, how the measurement was done. Secondly, we'll talk about the star and the planet, what they look like. Thirdly, we'll talk about Hubble's first measurements. These are the ones that suggested this planet might be a Haitian planet. A Haitian planet? That is, a planet that has an ocean of water and a hydrogen cloud. Then we'll discuss results from the James Webb Telescope that suggest possible life on that planet. Webb Telescope. And after that we will move on to criticism, because when I first saw the spectrum I said, hey, can you really jump to the conclusion so quickly that there is life there? Meanwhile, criticisms have also emerged. So I say let's get started, and please stay until the end. This is a video where I'm going to speak freely, and I would really appreciate it if you supported me by watching the videos where I speak freely, because, to be honest, it takes me quite a lot of time. We're talking about exoplanets, planets orbiting other stars. Note that this idea came from Giordano Bruno, following earlier scholars, including some from ancient Greece, who said that the stars in the sky are suns. Ori soarele nostru are planete. Attention, who like this in the stars above are attention, an idea that came from Giordano Bruno, who learned even from the ancient Greeks who the stars above foarte mare. Eu o să fac un video curând despre telescoapele are suns. Evoluția. Până atunci, telescoapele noastre, chiar cele spațiale, nu pot să mărească decât în apropierea stelelor, deci stelele apropiate. Atunci nu putem să detectăm exoplanetele doar mărind imaginile stelelor. Și de aceea folosim două metode. Metoda tranziției, în principiu, și metoda Doppler. Noi astăzi o să vorbim despre metoda tranziției, care se folosește. Attention, an idea that came from Giordano, who said this, learn the stars. Deci ocultează puțin steaua. Attention, from Giordano, who said this, perioadă de timp, cât timp planeta ocultează steaua. Și asta vedeți în acest grafic pentru fizica povestită. Aceeași metodă s-a folosit și la această exoplanetă, vedeți aici măsurătoarea. E foarte important să știm câteva lucruri din aici. The ancients who said that the stars above are orbitală a exoplanetei în jurul stelei. Why? Because we have one event, and after that we'll have another event after some time, and then another event, because each time the exoplanet passes in front of the star. We can also measure, and this is important, the size of the exoplanet, because the bigger the exoplanet is, the more light it blocks. And the ratio between how much light is blocked and the total intensity of the light is actually given by the area of the planet and the area of the star. And with this we can find out the area of the planet. Well, you might ask me, yes, but wait a minute. How do you know the area of the star? Here's another very interesting discussion. It's interesting because essentially we don't have to magnify the stars much to determine their area, but nowadays astronomers can determine the area of a star from the apparent brightness, the absolute brightness of the star, and very importantly the temperature of the star. In fact, the temperature of the star is what determines the absolute brightness through the Stefan-Boltzmann law. Well, I won't go into details here, but it's enough to know that astronomers can tell how big the star is without having to enlarge it. And in this way they can say how big the exoplanet is. We still need one more important parameter, which is usually the mass of the planet. Well, the mass of the planet is usually measured indirectly. Namely, let's say by the Doppler method, meaning the exoplanet orbits around the star, but actually it orbits around a common center of mass. Both the exoplanet and the star orbit around a common center of mass. That means the star moves past the line, forward, backward, and then the light coming from the star will be shifted sometimes toward red when it moves away from us, or sometimes toward blue when it comes toward us. So if we measure the light from the star, the spectrum, we will see an oscillation. The spectrum shifts sometimes toward red, sometimes toward blue. And it's very important that the amplitude of this oscillation is a measure of the ratio between the mass of the planet and the mass of the star. Because, you see, if the mass of the planet is very small, then this oscillation has a tiny amplitude because the star stays approximately in the center. It's true that a star has several exoplanets. So this Doppler motion has several components, but we can break down the motion into its frequency components, and of course, we're interested in the frequency component that has a period equal to the orbital period of the planet around the star. So basically from this motion we can also deduce the mass of the exoplanet. Finally, we're interested in the planet's atmosphere. We take advantage of the fact that when the exoplanet is in front of the star, the light passes through the exoplanet's atmosphere. And in this way, the absorption spectrum of the light passing through the atmosphere can be measured. Some calibrations are done there. Basically, the area of the planet is calibrated against the area of the star, and that calibration is subtracted. And if you subtract the two values, basically you're left only with the light that passed through the atmosphere, and that light that passed through the atmosphere, well, that's specific intensity. You divide it by the intensity of the light coming from behind, which gives you a kind of calibration from the star, and this way you can get the absorption spectrum of the atmosphere. And after the absorption spectrum of the atmosphere is measured, the molecules present there are identified because each molecule has its own distinct signatures. Some absorption bands at certain frequencies, and in this way they've found methane, water, and all kinds of other molecules in the atmosphere of distant exoplanets. Lately I've been working on my new book, and I realized something strange. Handwriting changes the way you think. It slows you down and makes ideas seem more real. And for writing, I used a hover pen, something that fits a science author very well. Why? Look at this.
Plutește literalmente pe baza sa cu ajutorul magneților, fără electricitate, la același unghi perfect de 23,5 grade, o mică trimitere la înclinația Pământului. Și în timp ce mă gândesc la cartea mea, mă surprind învârtindu-l pur și simplu. Este ciudat de satisfăcător.
This is the Interstellar Hover Pen, their main design, made from aerospace-grade aluminum. It comes in 4 different colors: Space Black, Starlight Silver, Neptune Blue, and Mars Magna, so it fits very... If you want, you can even add custom text to it. I made one for my daughter. It's the perfect gift for someone you care about. There's even a version with a real meteorite embedded in the tip, which is incredible if you think about it. Basically, you're writing with something older than the Earth. Personally, I'm impressed. It writes smoothly without needing to press, almost gliding on the paper, and there's also the Hover Pen Future, a 2-in-1 fountain pen and rollerball. This one also comes in different colors. If you want to buy it, use my discount code Christian. You get a 15% discount in the first 72 hours, and after that, the discount decreases. You can find the link in the description and in the first comment. Are you still with me? I was thinking that I started with these more educational things and that you might have already left, because we're about to talk about today's exoplanet and its star. These measurements were made for the very first time by this Kepler system, so this Kepler telescope, right? And the star is named K2K, probably from Kepler, K2-18. And the planet is named K2-18b. So you should know this about exoplanets, that exoplanets always have a letter B, C, or D at the end. And the term before that is actually the name of the star. This helps you, just like it helped me, to search for information about the star on the internet. And to find out that it's a red dwarf star that's more than 120 light years away from us. The star has a mass that's about half the mass of the Sun, but since it's a red dwarf, its brightness is only 2% of the Sun's brightness, so the star shines very faintly. What was discovered about the planet? Well, I read here that the planet has a mass 8.6 times greater than Earth's mass, a radius 2.6 times larger than Earth's radius, so essentially it could be considered a sub-Neptunian planet. I mean, we have the planet Neptune, which we know is larger than Earth. We know it has a solid core, right? But note that Neptune doesn't have a solid surface because from the solid core, there's a transition, so to speak, a gradual one, towards the atmosphere. So the planet Neptune doesn't have a solid surface even though it has a solid core. So the planet we're talking about is basically, or at least we expect it to be, a sub-Neptune planet. On the other hand, the planet's orbital period is 33 days. That means the planet orbits its star every 33 days. That means it orbits very close to its star. And we expected it to be heated by that star. On the other hand, we saw that that star is a red dwarf with a luminosity of about 2% of the Sun's. So, even though this exoplanet is close, its temperature is lower because the star is dimmer. Well, red dwarfs also have all kinds of other radiation, but these things are not being discussed here yet. Astronomers estimated the exoplanet's surface temperature and came up with something around. That means essentially it's a temperature close to the freezing point of water. That's where the interest came from, that the temperature is close to the freezing point of water, so in principle you could have water there even in liquid form. And then there was another thing, the average density of the planet, so the average density of the matter in the planet, if you calculate it, is quite low, which means the planet could have a lot of hydrogen. And then some people came up with this suggestion that maybe it's a planet, what in English is called a Hycean planet. What would a Hycean planet be? It would be a planet that has a solid core, an ocean of water, and a hydrogen atmosphere. Now, I have to tell you, when I looked up those articles, I was very interested to see the evidence that indeed there is hydrogen, and I looked for spectra that would show those absorption spectra of the atmosphere I was talking about that would show that indeed hydrogen was found there. But I didn't find any such spectrum that would clearly show me that there is hydrogen there. All I found were models based on the structure of how this planet would be built, on its mass, average density, and which suggest that there could be hydrogen there. So based on these density parameters, here I have such a chart where you can see all kinds of models for the planet K2-18b, the exoplanet. And on the horizontal axis we have the mass, on the vertical axis we have the radius, of course the masses of several exoplanets, the radii of several exoplanets. And the planet we're interested in, K2-18b, is represented with, well, a black dot there. From these density-based models, it turns out that, for example, this planet could correspond to the top line with that color which I think is magenta. It could have 94% an iron core, then 0.3% water and 5% hydrogen. There are also other similar models. You can see the first three lines, which essentially say that there is a core, then 0.3% water and hydrogen. So it could be a Hycean planet. However, the presence of water on the planet was directly confirmed by Hubble measurements, which used this transit method to measure the composition of the atmosphere, that is, to measure the absorption spectrum and identify the molecules that are there. And do you see the result here? Essentially, we are interested in that band which is around 1.4 micrometers, and which would be an absorption band of water. At the bottom it says vibrational band of water vapor. So this measurement by Hubble was one of those that suggested that, look, this planet could be a Hycean planet because, look, it detected water vapor in its atmosphere. The problem in spectroscopy, essentially, is that you see that in a certain range of light frequencies the light is absorbed, but you don't know exactly which molecules are responsible because there may be other molecules that absorb light in that range as well. In this case, the absorption spectrum of water overlaps with the absorption spectrum of methane. So, in other words, what we see in Hubble could be methane. It doesn't necessarily mean it's definitely water. Well, this exact thing was measured a few years later, just 2 months ago, since we're talking about recent results, by James Webb. Here we see the absorption spectrum of the exoplanet's atmosphere measured using the transit method, just as I explained. On the horizontal axis is the wavelength of the light, and on the vertical axis is a measure of absorption. On the left side, so the area from 1 to 2 micrometers, let's say, is the region that was also measured by Hubble. And the measurement results are the same, only this time the interpretation is different. Now these results tell us that there we don't see an absorption spectrum of water, but rather we see an absorption spectrum of methane. And why would it be methane? Because at higher frequencies, so between 1.5 and 2.5 and in this area as well, we again have some absorption peaks that match methane. And so it's much more natural to assume that what we see on the left is also methane. So basically, these measurements somehow cast doubt on the idea that that planet would be a Hycean planet with a lot of vapor and possibly water oceans, but instead say that there's a lot of methane. Now, methane is not very unusual in the cosmos. Saturn's moon Titan, if I'm not mistaken, contains methane, a lot of methane in its atmosphere. In fact, there are methane clouds there, it rains methane, and there are rivers and lakes of methane. So that's not something extraordinary. The interesting part actually of this measurement is the right side of the spectrum, which, pay attention, was fitted, modeled not only with the presence of methane in the atmosphere, but also with a new molecule which is labeled as DMS, that is, dimethyl sulfide in English, or sulfura de dimetyl, as I understand it's called in Romanian. Here you can see the spectrum, and we extend it to longer wavelengths, so the absorption spectrum of the atmosphere. And we see here that the respective researchers have modeled this time the peaks in the spectrum only with this molecule, dimethyl sulfide, sulfura de dimetyl. Now, why is this very interesting? Because on Earth, this molecule, dimethyl sulfide, is produced by living organisms. The concentration measured on this exoplanet of 1 ppm is a very high concentration, almost 1,000,000 times higher than the concentration of this DMS molecule on Earth. Here is an extended portion of the light absorption spectrum in the exoplanet's atmosphere, and there are measurements from 6 micrometers to 12 micrometers. And as you can see, these measurements were modeled by the researchers also with the DMS molecule, and in fact almost entirely with the DMS molecule. There is also another similar molecule, DMTS. When I first saw this, I wanted to make sure, so I searched for some information on the internet. Here is the absorption spectrum of the DMS molecule, dimethyl sulfide, and here you can see it. And, as you can see, there is an absorption peak at a wavelength slightly less than 7 micrometers, and one at a wavelength slightly greater than 7.5 micrometers. If we look at the original spectrum, we see the same absorption peak. So yes, it was modeled with the DMS molecule. In fact, I searched in vain because in the original article they also have the same fit. So you can see here the spectrum that was modeled with various molecules. But the most important molecule in this band, 6 to 12 micrometers, is the DMS molecule, which is the one with that light blue color. So you can see that it basically fits pretty well with almost the entire spectrum that's here. Alright, so the astronomer's choice to model the absorption spectrum with the DMS molecule, dimethyl sulfate DMS, isn't just something random, so to speak. It fits the spectrum match. The results and implications are remarkable.
Extraordinare.
This DMS molecule also exists on Earth, and on Earth it is produced only by living organisms. The concentration of the DMS molecule that was measured on the exoplanet, however, is 1,000,000 times higher than that on Earth. On the other hand, this molecule does not last more than a day in hydrogen-rich environments. So, in other words, if this planet had a lot of hydrogen, the chemists cited by the authors of that article tell us that this molecule would not have lasted more than a day. So should it be produced every day? Probably, they say, by these living organisms. The astronomers who published the results were so sure that what they measured there is the DMS molecule that they say the confidence level is at 3 sigma. So that means the chance of being wrong is 0.3%. The conclusion? On exoplanet K2-18b, the molecule dimethyl sulfide would be present, which essentially could be produced by life, by living organisms, and then life could exist there. But is that really the case? When I first saw the spectrum, I noticed that actually the measurement points, so the measurement data, are actually very scattered. And so I wouldn't be fooled, because what do astronomers usually do? Well, I did the same thing when I was a PhD student. I have a spectrum, and the spectrum is quite noisy, so I average it over a certain portion, and averaging is okay, and it's acceptable in science. But at some point, if it's done too much, it hides, so to speak, how large the errors are. So then I asked CGPT to extract the data from the spectrum and show them to me. So just the measurement data. And this is what you see here. This is the measurement spectrum, right? This time made by CGPT with the data from the measurement. And here you can see only the measurement points. And now, if we look here, how sure are we that there is an absorption peak around the wavelength of 6.8 micrometers or around 7.5 micrometers? How sure are we about the other peaks that are in the measurement? I didn't record. I'm back. Because the battery ran out, right? I started the recording, but I hadn't pressed the button. Where were we? Hold on a moment so I can put up that chart. Yeah, I think I know it by heart. We left off at this chart, which was essentially also in the original article, and which shows the measurement data of the absorption spectrum of the atmosphere on planet K2-18b. If we look here, we see that on the right there are a lot of measurement errors, and on the left there really do seem to be two absorption peaks, one around 7 micrometers, the other around 7.8 micrometers. Because of this, the researchers had chosen the dimethyl sulfide molecule. But watch out, now the criticism begins. That's what the critics say, but if you look at the original article, they actually made a selection from only 20 molecules. Why did they say it has a 3 sigma confidence level? So an error of 3 sigma, meaning less than a 0.3% chance for it to be something other than DMS? Because they only considered 20 molecules in their modeling. But why 20 molecules? There are thousands of molecules that could exist in exoplanet atmospheres. Why not others as well? The researchers who originally made these measurements said that they started out with the idea that this is a Hycean planet. That is, it's a planet with a solid core, an ocean of water, and an atmosphere rich in hydrogen and water vapor because of that ocean. But as we've seen in the newer measurements from the James Webb Space Telescope, there's actually no water there, but methane instead. So it could be a different kind of planet than a Hycean planet. There are also other types of planets. You can see in this graphic, on the left side, a Hycean world, which has a solid core, water, an ocean of water, and a hydrogen-rich atmosphere. But there are also, just here in this graphic, 2 other types of planets, which are essentially called mini-Neptunes. And the geology on these planets, they say, also determines what happens in the atmosphere. And that's what we see in this graphic. Here we see 5 possible concepts for the atmosphere of the exoplanet K2-18d, which also take into account, importantly, the geological structure. But the point critics make is that there are many more molecules in the atmosphere, and that those who did the modeling should have taken these worlds into account as well, not just the Hycean worlds. For example, the same molecule, dimethyl sulfide, was found on comet 67P Churyumov-Gerasimenko. Here you can see the spectrum, and in pink the presence of the molecule is indicated in that spectrum, in the mass spectrum this time. So if this molecule exists on a comet that we know doesn't have life, that means it can also be produced by abiotic mechanisms, meaning mechanisms that don't involve life. Moreover, the same molecule was also found in a very dense molecular cloud, G0693. I looked at that article, and here you can see some of the results. And they say that, well, by using the radio method, so this time it's not optical spectra but radio spectra, they managed to detect the presence of the DMS molecule in that molecular cloud. To be honest, these results don't seem that conclusive to me, Because if you look closely at each of the results from the radio spectrum, at each smaller image, you'll see that there are a lot of molecules being used to model what's being measured. And so yes, let's say the spectrum associated with the DMS molecule isn't really that prominent. Okay, and there are also experimental studies that have demonstrated the synthesis of the DMS molecule by ultraviolet irradiation of some planetary atmospheres modeled in the laboratory. I haven't looked into those studies further, but I found this reference. Critics say that this molecule could, for example, be produced on a planet that has a global magma ocean, or on a planet where there is an atmosphere dominated by a gaseous composition, both of which essentially are hostile to life, so through abiotic processes. I'll let you draw your own conclusion. I just want to share my opinion. I don't have a conclusion, I have an opinion. It seems to me that it's extremely difficult to say with certainty that the molecules you discover on other exoplanets through the transit method are actually those specific molecules, and that those molecules are produced by life. And I think that, after all, this is the essential message of today's video, because I imagine that such news will appear in the future as well, and that's normal because we want this kind of news. But what I wanted to show with this video is that we still need to be careful and aware. We need to be aware that these spectral measurements of the atmosphere are essentially measurements that give us an indication about the presence of certain molecules. And the chemistry of everything, the geology of the planet, of the atmosphere, yes, it's much more complex and, well, we need many more measurements. We need to realize this. And I forgot to mention one more thing. Yes, the measurements were made by James Webb in the infrared, because indeed, the vibration and absorption spectra of molecules are generally in the infrared. And so this ability of the James Webb telescope to measure in the infrared is very welcome. And if you still remember the hoverpan, you get a 15% discount in the first 72 hours, and after that the discount decreases. You can find the link in the description and in the first comment. Until next time, I am Christian Presura, Physics Explained. I wish you all the best. Goodbye.